Hello, you absolute legends. After hiking and long walks on the beach, doing some scaffolding and graphing are some of my favorite activities. The ideal gas law incorporates the four measurable quantities of a gas and relates them to one another. Because through physical observation, through observation after observation, we know that these things are related to one another. I want to talk about the structure of the formula using scaffolding, and then talk a little bit about how the graphing and the experiments that got us to the ideal gas law. So the ideal gas law, I said, contains the four measurable quantities of any gas. There are other quantities of a gas you could measure, but there are four quantities present in the ideal gas law: PV, pressure, volume; N for the number of moles; R, which is a gas constant, not a measurable quantity, but it is a constant; and then T, temperature. So there are uno, dos, tres, cuatro measurable quantities in this formula right here. And scaffolding, or focusing on the units, I think is very, very helpful when using formulas like these, because letters P, V, N, R, T, okay, all right. So what I recommend you do with these formulas is you write in the units that you are meant to use with these. So pressure, you would measure pressure in ATM. You would measure volume in liters. N for number of moles of the gas. And T for temperature, we would measure in Kelvin or Celsius. Let's keep that as Kelvin right here. So these are the four measurable quantities you can measure about a gas at any given time, the state properties. The pressure, its volume, how many moles of gas are present, and the temperature of the gas at the time right there. Now, this unit R, this constant R, is one of the most variable constants in science, because you can measure temperature in many different ways in Celsius, Fahrenheit. You can measure volume in gallons, milliliters. You can measure pressure in kilopascals. As you change these units, the unit of R and the numbers for R always get messed around. Do it. Google, pause the video right now, Google Wikipedia gas constant, and you will see a table on the right-hand side of a bunch of values. Now, you need the value that matches these units. How do you know what that is? You treat this like a scaffold where you solve for R. So we have to get R by itself. So let's divide both sides of the equation to get R by itself. We are left with the units of R that we're interested in being ATM, pressure, times volume, divided by moles times Kelvin. You see how complicated this unit is? It has four different units based in there. Now, this is only a part of the puzzle. This constant R has a value associated with it. 0.0821 ATM times liters, moles times Kelvin. That is the full value in units for R, the gas constant. I said there was some graphing involved in here. Plotting experimental data with graphs is how we got this number 0.0821. I'd like to show that. Now with graphing, we in science like to plot things in a straight line. So anything that can be plotted in a straight line is what we're interested in. If we think it's going to be a straight line and it plots out to be a curved line, that's a discovery worth writing a paper about. If it's supposed to be a curved line and plots out to be a straight line, that's also a discovery worth writing about. The generic formula for a straight line is y equals mx plus b. M is the slope of the line, y is the value on the vertical axis, x is the value on the y-axis, and b is what's termed as the y-intercept form. Now, I maintain to you that PV equals nRT is written in this format. And the slope of the line is the gas constant R. The slope of any line, M, is defined by the change of Y divided by the change of X. Let's remind ourselves what the Y and what the X are in PV equals nRT. PV equals apologies. I've tried to rearrange this so that way it's much more visible vertically, what I'm trying to display here. The Y values are the measured values of pressure times volume. On the x-axis, we have number of moles times temperature. Now, in PV equals nRT, there was no plus anything, so we just made it plus 0, which is effectively not leave it on there. And I maintain that the slope of the straight line is m, or r, the gas constant. So what this means is when people took a cylinder or a balloon of gas and they measured these 4 things every time, the number of moles, the temperature, the pressure, and the volume, they would take the values for the pressure and the volume, multiply by one another, and get a data point. They would take the values for number of moles in T, multiply by each other, and get a data point. And do that again and again and again and again, and a straight line was observed. The slope of that line is, you guessed it, 0.0821, and any graph is delta y over delta x, PV divided by NT. Now, this was a significant discovery based on experimental data and graphing. And what was observed is in this combination of this being on the y and this being on the x, that's when you got the straight line. If you did other things and you tested the experiment, you would not get a straight line. It would not be predictive of Mother Nature's habits, therefore less useful. Remember, one of our big goals is to predict the quantum of the universe, to predict what Mother Nature is trying to do, will do, or what doesn't want to do. This is about the ideal gas law, scaffolding with units, so you never have to remember the units of R. You can always rearrange. And also the graphing is meant to display how this formula and how these values in units were observed and measured so many years ago. Have a great day. Thank you.